Okay, we're being asked to set up a triple integral that finds the volume in the first octant inside the cylinder and below the cone. What I'm going to do is draw the whole picture first, and then we'll look at the first octant. The cylinder x squared plus y squared equals 1 is what we normally call a cylinder, because z can be anything. The cone starts here, and then comes down like this, comes down like this, and goes over like that. So if we weren't restricting to the first octant, we would just be looking at that region right in there. All right, so I think we have enough now that I can actually draw maybe a picture of what we're actually being asked for. So what I'm going to do is I'm going to go to the first octant. I'm going to draw as much of the cylinder that's in that first octant. So it's going to go like this, and go like this, and go like this, and down and over like that. That's the cylinder part. The cone part, remember that starts here, that goes up like this, that goes over like this, and then it hits the top, and this is the chop of the cone that we want. Just a reminder that what we really want, right, is the volume that's right there. So I'm going to start setting up the integral. I know it's going to be a triple integral. We could start drawing lines in any direction. I'm going to draw lines that are parallel to the z-axis. If I draw lines parallel to the z-axis, right, line comes up, hits the region right there, keeps going, we're in the region, in the region, in the region, leaves the region right there. Now all I really care about, because I'm going to be doing dz first, is what z is as it enters. Well, it's entering at the xy plane when z is 0. It's leaving when it hits the cone, right? So this is z equals the square root of x squared plus y squared. Now, I'm going to look ahead just a little teeny bit. When we smush, what we're going to be seeing is just a quarter of the unit circle. And the nice thing about the quarter of the unit circle is if I was to smush to polar, right, the unit circle actually has a very easy integral. So this is what I'm going to do. I'm going to say that z starts at 0 and then ends in polar at r. So I'm going to put a little r right there. It'll make it easier. Now normally I would put dx dy, but I've decided to smush the polar. So I'm going to go to r, dr, d theta like that. I can start drawing rays, right? Just so we're in the habit of drawing rays, this one's absolutely trivial, right? The rays enter the region when r is 0. The rays leave the region when r is 1. And I only needed to actually use thetas that start at 0 and end at pi over 2. And that's the integral I want to do.